as a last step, we will show the existence of a function omega which has valuation at pi exactly ni. These ni's again are given. So let me say it by the notation so far. And its proof will be, again, kind of an extended version of the proof of the first lemma. In this case, we choose a function whose valuation at I is equal to minus ni. And we consider the K-linear map from the Riemann-Roch space of this divisor or the Riemann-Roch space that contains functions which has described poles and zeros, counted their multiplicities, from the product of the residue class fields. And like in the lemma, we will identify this function by regarding the evaluations of this function times this ti at pi's. This is w times tr of pr. Let me write it properly. And as a sketch, we can see that its kernel contains the functions almost have the same poles at q, but its zeros has bigger multiplicities. And again, if n is large enough, by the Riemann-Roch theorem or its consequences by the Riemann theorems, then indeed we can see that this K-linear map gives us surjection, of course, by applying the first isomorphism theorem. If equality, then phrase onto, and the dimension of the A space of, let me denote it, this divisor by A, it's, so I mean the dimension of the kernel in this case is equal to the sum of the extension degrees of the residue class field, so that means sum of the degrees of the given places. And by using this onto the property of being onto, we can consider the pre-image of the vector of 1 in this in the Riemann-Roch space of this divisor. So that means we can choose omega in the L space of, maybe it's, I am sorry for the notation, let's call it A, let's call it B, and let's write it B. And in this case, we can choose a function in L of A. So that means that VTI minus 1 has valuation bigger than or equal to 1. And this function has valuation at V1 as 0. And again, by the properties of the discrete valuation maps, we see the existence of the functions which has pre-described poles and zeros at p given pi's. And finally, by using this tree lemma, let me call it sketch of the proof of the strong approximation theorem. First, we can choose an integer which is always strictly bigger than the given integers ni's. And by lemma 2, we can choose a function in O that satisfies the property which is given in lemma 2. And finally, again, we can choose a function omega. Let me call it as in lemma 3. And if we set, by regarding these functions y, i's, and omega, if we set the function z as a linear combinations of these functions, and that we can see that it's also an element in the subring we defined in the previous video. And finally, we can check that the difference between the z and xi has valuations at pi's or i's. Here we only replace the z by the setting. And in this term, by the assumption, has valuation ni, and this term has valuation which is bigger than or equal to s, and by the assumption which is statistically bigger than nj, and this term has valuations again strictly bigger than or equal to ni. And then we can see the existence of the desired function.